In the previous few videos, we talked about the major data structures provided by TensorFlow for storing different types of information that are related to the neural network. In this video, let's put those data structures into use and try to solve a toy problem, which involves only one neuron. And once we have solved this toy problem, you will see that it is actually quite straightforward to apply the same template, to apply pretty much the same template to the MNIST handwritten digit recognition problem, or even to sort of even more complicated nonlinear problems. It's pretty much the same template actually. The diagram of our single neural network looks like that, looks like this. So we have three inputs, x0, x1, and x2. The logit z in this neuron is just a weighted summation of these three inputs with weights given by w0, w1, and w2 respectively. And the output of this single neuron equals to the logit. So y equals to z. And there is no nonlinear function used inside of this neuron, right? We are using a linear function, right? Y equals to z is a linear function. It's not a nonlinear function. So this neuron doesn't have any nonlinearity in it. The bias term is accounted for by the input x0, which has a fixed value of 1. So we can write the neuron output y, because y equals to the logit, right? And then the logit equals to a weighted summation of those three inputs. So it's w0 times x0 plus w1 times x1 plus w2 x2, right? And account for x0 being fixed at the value of 1, so it's w0 plus w1 x1 plus w2 x2, right? That's the output of the neuron. We don't know that we don't know what are the best weights for this single neural network, right? We don't really know what are the best W's. But what we have is 5 examples from our training dataset, right? So when the input x1 equals to 0.2 and x2 equals to 0.7, the ground truth output is 2.28. And when the input x1 equals to 0.5 and the input x2 equals to 0.1, the ground truth output is 3.27. Right? So we have 5 this kind of examples. And so what we can do is to put those ground truth values, ground truth output data, into one array, say y, right? And this y is just a vector with is just a array with like a one-dimensional array with like 5 numbers in it, 2.28, 3.27, that kind of thing, right? All 5 numbers. And all the numbers that's being multiplied with the different weights are being put into another 2-dimensional array. That's called a big X, right? So big X is the number that's being multiplied to each of the W's. So W0, the number multiplied with W0 is always 1. So it's 1, 1, 1, 1 for the 5 example. And then for the first example, the number multiplied with W1 is 0.2. The number multiplied with W2 is 0.7. And then that's the first example. So it corresponds to first row in the X matrix. And then for the second row, it's 0.5, 0.1. And then 0.15, 0.4. Right, so basically we are moving all the numbers that's multiplied with each of the W into this matrix that's called X. And then all the W's, all the unknown W's can be put into a vector that's called W0, W1, and W2. So that's another vector, W, right? So basically for those 5 training examples, this very simple linear neuron. So for every set of input and the ground truth output, we have 5 of them. And the calculation done by this kind of a single neuron for these 5 data sets, for these 5 example data sets, can be actually sort of represented using this kind of a matrix and vector representations. If you actually think about it, it's this matrix representation actually represents 5 runs of this single neural network, every time with a different set of x1 and x2, and every time it produces one different ground truth, right? So this kind of this matrix with 5 rows and 3 columns, and this vector with 5 rows, and this vector with 3 numbers in it, actually represent, if you actually put them together, it actually represents 5 different runs of this particular simple neural network, right? And each row represents 1 independent run of this neural network. And these 5 runs, you can actually sort of represent the 5 runs in a sort of very abstract way by doing this kind of thing. It's a matrix multiplied with this vector. It's a matrix vector multiplication. If you studied linear algebra before, this might look very familiar to you, but if you have no background in linear algebra, then you can think of this kind of multiplication as, so you can think of it as 5 different runs. Every run is 1 row of x multiply 1 column of w. So it's 1 multiply w0, 0.2 multiply w1, 0.7 multiply w2, and then you add those products, the 3 products together, you get 1 output. You get a 1 output, and then you do this kind of thing 5 times. You get 5 outputs. That's going to correspond to the numbers in this y pred. We use pred to represent the prediction, right? So if you assume a certain value for w, then you can do this kind of multiplication, matrix vector multiplication, using that assumed w value, because the x value is fixed, right? And then you're going to generate a vector or output, 5 outputs. You're going to generate 5 outputs that's predicted using this assumed w value, right? And then you can compare this predicted y values with the ground truth y values, and then you can use that difference to set up a gradient descent method to minimize that difference in order to actually improve your estimated w, right? And if you have studied linear algebra before, it's this kind of problem is called linear regression, right? Our goal in this linear regression problem is to find the best set of values for w, so that the difference between y pred and the ground truth y is as small as possible. And we can quantify the difference. We can quantify this difference by using one number, one scalar, which is actually the summation of the squares of the subtraction between the corresponding elements in y pred and y. And this number is called the mean squared error, or MSE, the mean squared error. Right? And we will try to solve this problem in several different ways by using TensorFlow. If you have studied linear algebra before, you might still remember there's a solution to this particular linear regression problem, which is given by the so-called normal equation. The thing that you see here is the so-called normal equation. And w hat is sort of the best estimate of the w value. And you can compute it by doing this kind of matrix vector operations. So the capital T on the superscript represents a transpose. A transpose merely means that the rows becomes the columns. So the first row is going to become the first column of the of xt, and then the second row becomes the second column. Right? If you are in computer science, you may have some kind of image rotation problems, right? But this kind of matrix transpose is not exactly the same as image rotation. It's in image rotations, it's this value is going to come to this point or something, right? But here it's a row and column are being sort of switched. So first row becomes first column, second row becomes second column. It's a different kind of calculation. And then you sort of see this -1 as the superscript, which actually means a matrix inverse. Again, it's a linear algebra thing. So if you have no idea about what this kind of thing actually is and how to compute it, you don't have to worry about it, because TensorFlow is going to take care of it. And TensorFlow is also going to take care of the transpose also. TensorFlow can do the transpose automatically. It can do the inverse automatically for you. Right? You don't really have to worry about those calculations. And how do you actually get this kind of normal equation, right? What's actually the reason for saying that this particular complicated equation actually gives you the best estimate of all the weights? Why is that, right? We'll come back to the mathematics behind the theory in later videos, after we have finished talking about deep learning, right? So TensorFlow can certainly do those operations for you. Those linear algebra operations can be done very efficiently in TensorFlow. And if you have both GPUs and CPUs, TensorFlow will automatically distribute the load if the matrix are kind of big, right? And but if we don't know enough about linear algebra, at least we haven't actually talked about these kind of normal equations yet, right? If we don't know enough about linear algebra and really have no idea about how this expression is obtained, TensorFlow also allows us to solve this kind of linear regression problem through various flavors of gradient descent, right? And this kind of methodology is actually applicable not only to linear regression problems, but also to much more complex nonlinear problems, such as the MNIST handwritten digit recognition problem, right? So the deep learning methodology offered by TensorFlow is actually more general than this normal equation. So once we understand how we actually solve this problem with the kind of a deep learning methodology, then you can decide if you want to go back to learn this kind of a more specific technique that's only applicable to linear regression problems, or if you just want to stick with this sort of more general methodology. So let's go back to Spider and let's try to implement the solution to this problem using a few different approaches. And let's start by constructing a few NumPy arrays for representing the input data matrix X and the ground truth vector Y. Right. So here I have already finished writing up the codes for constructing the NumPy arrays, basically. So the number of examples of our training data set is 5. So the number of rows of the X matrix, n row, is set to 5. And then we have 3 weights. So the number of columns in the X matrix, n col, equals to 3. And we have a 2-dimensional NumPy array, actually, for representing the input data x1 and x2, and also with the bias x0, which is fixed at 1, right? So here all the ones represents x0, actually, and then 0.2, 0.7, 0.5, 0.1, all those numbers were taken from this particular matrix. 0.2, 0.7, 0.5, 0.1, right? 0.2, 0.7, 0.5, 0.1. So the input data with bias, this particular NumPy array, is exactly a 2-dimensional array that's sort of with the content identical to that X matrix we are seeing from the PowerPoint. And it's got like 5 different rows. This is 1 row for the first example in our training dataset. That's the second example. That's the third, fourth, and then the fifth. So it's got like 5 rows. Every square bracket is a row, actually. And inside of the square bracket, every number is a column. And they are separated by using a comma. And then we also have a 1-dimensional NumPy array for representing the ground truth vector. And also with like 5 different numbers in it. That's just like, we're reshaping it. We're reshaping this particular 1-dimensional array into a shape that's 1 column. And a minus number for the row number is asking NumPy to automatically calculate what's going to be the row number. Right? It's supposed to be 5, right? So you give it a minus number to ask NumPy to automatically compute the row number for you if you actually fix the column number at 1. we have not talked about NumPy in this sequence of videos yet, right? But I'll try to include some discussions about the basics of NumPy in my hands-on start to Python sequence. So we will not cover NumPy here, right? But you can sort of see I have imported the NumPy as NP. So there is some sort of usage of NumPy throughout this example. Now let's first try to implement the solution using the normal equation, right? Even if we don't really understand the mathematics behind it yet, later on, after we finish talking about deep learning, we will come back to this linear regression problem and try to understand better the mathematics behind it, right? If we have time or if we have enough material. So let's first define two tensors to represent the matrix X and the ground truth vector Y. And we will just use TensorFlow constants. So here, before I actually insert any nodes into the default graph, let me reset the default graph. And then we can insert some nodes into it. So we're going to use constant. So input data with bias. We're going to use this NumPy array that we define here to initialize our TensorFlow tensor X. Let's call it X, right? The constant. And then let's supply a type, d type equals to float. Let's use tf.float, float 32. And then let's give it a name, right? And then y equals to tf constant. This time it's ground truth. And then d type equals to tf.float 32, and name is going to equal to y. Right. So big X corresponds to the big X here, right? And then small y corresponds to this small y here. That's the ground truth vector, right? And now we can just use TensorFlow to construct a W hat by typing in the normal equation as it is on our PowerPoint slide, just like that, right? And all those transpose and inverse thing can be sort of computed by using TensorFlow, right? And so because we are using the transpose quite often, so let's define a separate tensor. It's going to equal to tf dot transpose x, right? So xt, that's the transpose of x, is obtained by using the tf dot transpose function. We just apply this function to x, the tensor that we have defined here. Then we get the transpose of x, and then w hat just equals to tf dot matmul tf dot matmul. Matmul means matrix multiplication. Again, it's a linear algebra thing. If you have no idea about how to do matrix multiplication, you don't have to worry about it, because TensorFlow takes care of the linear algebra matrix multiplication for you. So you don't have to sort of do the calculation by yourself or write your own code for doing that. And then matrix inverse. This matrix inverse function is going to take care of the -1 in the superscript. And then tf dot mat mul xt x, and then xt, and then y, right? So you can sort of compare it with this expression here and see if it's indeed consistent. So it's xt times x, and then takes the inverse, right? So it's xt times x matrix multiplication, and then -1 is tf dot inverse, tf dot matrix inverse, right? So it's the inverse of xt multiply x, and then we have to sort of multiply with x again, x transpose again, xt again, right? Matrix multiply with xt again, and then the result is going to be multiplied with the ground truth y, right? Another matrix multiplication, right? So that's exactly the value for w hat. That's the normal equation. Um, so once we have finished constructing the graph, so everything here that we have done so far is actually constructing the graph. We haven't actually evaluated the graph yet. So to evaluate the graph, we have to open a session, tf.sc session as, and now we can just paste the w. We can just call the eval function on w hat now, right? And the eval function is gonna return a numpy array, and then we can just print best w and see what the best available w's are. I have a few typos. Transpose, it's not transpose. Right, so it's giving me the solution now. It's about 2.5 for x for w0, 1.7 for w1, and about minus 0.8 for w2. So it's 2.5, 1.7, and minus 0.8. That's our best estimate of w based upon this particular normal equation and the training dataset, right? So that's by using the normal equation stuff. Let's write a comment here. Now let's try to use the batch gradient descent, or BGD, which we talked about in the 7th video. In practice, when we have more than 5 examples, suppose we have like a 50,000 or 5 million examples, right? Then we probably want to use a mini batch, right? But for now, let's just use the batch gradient descent because it's easier for us to demonstrate some of the key concepts. So now let's try to use the gradient descent based methods. Right. So first we will do this by manually computing the gradients. And then we will use the TensorFlow's auto-def feature to let TensorFlow compute the gradients automatically. And finally, we will use a couple of TensorFlow's out-of-the-box optimizers. Right? But first, let's add a few more nodes to the default graph. We will need a TensorFlow variable to store the weights w. Right? When we were talking about the variables, we were saying that the variable is like the ideal data structure for storing the weights. So here we're going to use the TF. We're just going to use the constructor instead of using the get variable. But in practice, you might want to use a get variable. The reason I'm using the constructor here is because it's easier to do that. Uniform. And then it's going from minus 1.0 to positive 1.0. And then with the name equals to w. Right. So it means that the variable w, when we try to initialize this variable, it's going to be initialized using random numbers that's kind of uniformly distributed from minus 1 to 1. Right. And then w is going to be a, so you sort of see a list, Python list here. That's nco. Nco equals to 3 because we have like 3 different weights, right? W0, W1, and W2. And then it's 3 rows and 1 column. Right? That's the shape of our W variable. It's a rank 2 tensor, with the first dimension given by n code, that's 3, and then the second dimension given by 1, right? So next we can compute the y pred. We can compute the y pred. If we have a sort of estimate of w, we can compute the y pred by doing this kind of matrix multiplication, right? So we can compute y, that's pred equals to tf dot mat mal x w, and then we're gonna give it a name. It's called a prediction, right? So this name, so we are actually calling the matrix multiplication routine, right? Matrix multiplication function takes 2 inputs. That's the 2 matrices that we're gonna multiply. But it also takes an optional 3rd input, which is gonna specify the name of the result of the multiplication, which is y pred. Let's just call it a prediction, right? And then don't forget we have to sort of quantify the kind of difference between the predicted y and the ground truth y, right? So the first thing we're gonna do is to actually compute the difference. So error equals to y underscore pred subtract y. So this is a element-wise subtraction between 2 tensors, between the elements inside of the 2 tensors. It's an element-to-element subtraction, component-wise. And then we're gonna use the so-called mean squared error, or MSE. Right? It's just a summation of the squares of individual errors inside of the 2 vectors, inside of the vector, right? Inside of the error vector, basically. So how do we actually compute the MSE, or mean squared error, right? Let's call it MSE. MSE equals to TF dot reduce sum. So this reduced sum is gonna do a summation along a certain direction or along a certain dimension of a tensor, right? If we sort of just use a reduced sum, no, it's not reduced sum, it's reduced mean. Let's use reduced mean. Sum is just going to do a summation, but mean is going to also take the summation first and then divide by the total number of elements inside of that summation, which is actually a better estimate. And then tf dot square u ARE tf square error name equals to MSE. This is the mean squared error, MSE. So we first square each of the element inside of the error tensor. The error tensor is just element by element subtraction, element-wise subtraction between y pred and y. We're just squaring each of the element inside of the error. And then this tf dot reduce mean is going to do a summation of each of the element inside of the squared error tensor, right? And that's going to be our indicator, or the kind of a quantification of the differences between the prediction and the ground truth. And that's all the nodes that we're going to add to the graph, to the default graph. And now we can introduce 2 hyperparameters for our gradient descent method. One is the so-called learning rate. We have seen how the learning rate before. Let's just fix it at 0.01 for this particular example. And then there's another number that's also a hyperparameter. It's the number of epochs. Let's call it n underscore epoch. Let's give it like 10,000 or something. Right. So we will talk about the epoch when we talk about the mini batch gradient descent in the next video. But for now, let's just consider this number n epochs as the number of steps we're gonna walk in the negative gradient direction. So let's just consider this number as the total number of steps we will take along the negative gradients, right? when we talk about the mini batch gradient descent, we will sort of talk about the epochs in more detail. Right? But for now, let's just consider epoch as just an iteration number. And in our first example, that's going to use the gradient. Let's compute the gradients manually, right? And here we will again use the results from linear algebra. If you are not familiar with those equations, it's okay, because we will come back to the mathematics behind it in later videos. But for now, let's just use the results, and we're gonna define a new node that's gonna equal to 2 divided by n rows times tf dot mat mul xt error. Right, it's basically the transpose of the x tensor times the error tensor. A matrix model, error tensor is defined here. Right, xt is defined here. Right, so both nodes already exist. It's not n rows, it's n row. Okay, so it's n row. That's going to be our manually computed gradients. And once we have the gradients, we can define a TensorFlow operation. We can define a TensorFlow operation to represent the process of moving the weights in the negative gradient direction by one step. Right, here we can define a training op equals to tf.assign ww subtract learning rate times gradients. So here the tf.assign function creates a node that will assign a new value to a TensorFlow variable. And the new value here is w subtract learning rate times the gradient. And this new value is assigned back to w. So because w is a variable, so we are allowed to make changes to its content, right? And this dot assign function is going to return something that's not exactly a tensor, but it's actually an operation. In the computational graph, every operation is also represented as a node, right? But their shapes might be slightly different, right? So when we're looking at the different high-level components of a graph, this multiplication is an operation. This add is an operation, right? Those are operations. So here by tf.assign is just creating another operation. It's another kind of a elliptical circle on this particular graph. We're adding one more sort of operation to that graph. So and in this operation we're assigning this new value to the old value. So we're basically replacing all the values inside of W with this newly computed values inside of this expression, right? And now we can actually open a session to train the model. So with tf.session as says, right? And then this time we have a variable now, right? In the previous run with the session, there's no variables. Everything is just the straightforward tensors, right? But here we have a variable, so we cannot forget to initialize the variable. And we're going to just call the tf global, a global variable initializer, to initialize everything, even though we have just one variable. So, but let's still just do that for the convenience of it. So for, and then we're going to do an iteration. So I was saying that we can think of this n epoch as the number of steps we want to take along the negative gradient, right? So for, we're going to write a loop for epoch in range n epoch. And then within this loop, we're going to just run. We're just going to run this training op. It's not n epoch, it's n epochs with a plural. And suppose we want to monitor the progress of our training. We want to print out something, but we don't want to print out we don't want to print out for every epoch. We want to we want to print out for every epoch that modulo 100 equals to 0. So we want to have one printout for every 100th epoch. So we're going to print and then we're going to print MSE. MSE dot eval, because MSE itself is a tensor, so we have to call the eval in order to actually get a sort of NumPy array that's printable. And then after the for loop, we're done with our training, and we can get our best W equals to W dot eval, and then we can just print out best W, right? And that's going to be our gradient descent implementation using a manually computed gradient. Right? Again, it's a linear algebra expression, so manual gradient. Let's just run it, and we can sort of see the printout in the console. We got a number that's close enough: 2.5, 1.7, minus 8, minus 0.8, right? So if we increase the epoch number, supposed to like a double it, then we'll probably get closer. Right, it's indeed closer. Right. So that's going to be our manual gradient implementation. Right. So, but TensorFlow can automatically evaluate the gradients for neural networks with arbitrary complexity by using the back-propagation algorithm. Right. So to use the TensorFlow's automatic gradient calculation capability, all we need to do is to actually replace this manual gradient with one line of code. Gradients equals to, we're going to call tf.gradients, right? And then it's going to take two mandatory inputs. One is the thing that you want to take a derivative of, that's the MSE, and then the thing that you want to take a derivative with respect to, that's W. So here we are actually taking the derivatives or gradients of the MSE, that's the mean squared error, with respect to the weights W. The return value is going to be some kind of list, right? And what we want to do is to take out the zeroth element of that list. That's going to give us the gradient. And if we use the automatically computed gradients, this automatic gradients is applicable not just to this linear regression problem. It can be applied to any kind of a neural network, right? But this manual expression here is only applicable to linear regression problems. Even when only when your sort of neuron has no nonlinear function in it, this thing works. This expression works, right? This linear algebra thing works. But this thing is generally applicable. It's applicable to neural networks of any kind of complexity. And then let's run it again. Right? Still a very close result, right? So here we need to tell TensorFlow what exactly we're actually evaluating the gradients, right? So the two mandatory inputs are kind of essential. It's really important. You have to tell the gradients function, the variable and then the independent variable. So it's the derivatives of MSE with respect to W, right? So these two inputs are mandatory. So if we do not change the rest of the code, and we still get the correct results, right? All we did was to change this manual gradient, which is only applicable to linear regression problems, to this automatic gradient, which is actually applicable to any kind of a neural network. And then TensorFlow not only provides automatic differentiations, it also provides a number of out-of-the-box optimizers, including the gradient descent optimizer. And we can replace those explicit gradient calculations and the training up here with an optimizer. So basically we can just replace these two lines replace these two lines with a so-called optimizer. Let's define optimizer equals to tf.trend.gradient descent optimizer. And then this gradient descent optimizer function is going to take a mandatory input that's called the learning rate. And then we're going to supply it with our learning rate here. Let's right. And that's going to give us the gradient descent optimizer with the learning rate set at 0.01, right? And then we can derive a training up from this optimizer. All we have to do is to tell the optimizer which tends to minimize, actually. Well, we want to minimize the MSE, right? So the optimizer itself is going to sort of decide how to actually minimize MSE using the gradient descent method, right? So it's going to decide how to compute the gradients. It's going to sort of call the gradients function for us, right? And it's going to do everything automatically. So again, if we just run this code without any other changes, we should be able to actually get the correct results. Yeah, that's also correct, right? And there are more than one optimizers. So gradient descent optimizer is just one optimizer inside of a very large collection of optimizers, right? Suppose you want to experiment with different kinds of optimizers. So all we have to do is to just replace this one line. Suppose we want to replace the optimizer with something that's called a momentum optimizer, and then it's going to require a learning rate. And then it's also going to require one additional input that's called a momentum. Let's give it 0.99, right? Let's see what's going to happen. So the mean square error has reduced to like almost nothing. Okay, so 2.5, 1.7, minus 0.8. So this one is actually most accurate. It's most close to the true solution, actually. So there are multiple optimizers, and it will take some experiments. It takes some experimentations to actually find the best optimizer for your specific data set. But those experimentations can be done very easily just by replacing this line. Okay. So this is linear regression, and in the next video we're going to talk about a mini-batch gradient descent for the same linear regression problem. And then once we understand how this thing works for mini-batch gradient descent, it's kind of easy to apply the same kind of approach to the MNIST handwritten digit recognition problem.